Okay, so there are a couple of ways that a matrix, a vector, pretty much a vector, can be linear. These vectors can be linearly independent, okay? And or they are dependent. So pretty much the easiest way for us to do these is to go through the special cases, which A and B are kind of special cases. C is kind of normal, and I think I'm gonna start with C, okay? So what you're doing when you're determining if they're linearly independent or dependent is this vector is like x1 and this is x2. Okay, and so what you're doing is you're kind of turning these back into some sort of linear equation. So this is really like x1 uh, minus 4x2 equals 0, and 2x1 plus 10x2 equals 0. So what we need to try to see when they look like this, when we have a coefficient in front of each variable, we need to see if they're independent of one another. And the way we do that is we go, okay, can I take this first row, this first equation, and multiply it by something, by a scalar, by like 2, and get the second equation? If I can, then they're dependent. If you can make those equations equal one another, like when you're doing reduced row echelon form, and you go to zero things out, if you can make them turn into themselves, one row turn into the other row, then they're dependent because they're really the same line. They're the same equation. They're the same row. So they would be linearly dependent. Okay, if you can't, if they're their own self, like I can turn 1 into 2 by multiplying by 2, but then I have to multiply the negative 4 times 2. It doesn't become 10, it becomes negative 8. So 210 is not a multiple of 1 negative 4. Therefore, these are linearly independent. Okay, now they also, and usually when we write it as the matrix, I should chop that off. We don't put the zeros on there, okay? We have 1, 2, negative 4, 10, okay? Or 1, negative 4, 2, 10. Because, and this is what? This is a square matrix. It's a 2 by 2. So that's a key right there. Because, to do a reduced row echelon form, I kind of need to have it in a square matrix 2 by 2. So if I look at D right now, I can already tell that these are going to be linearly dependent. Here's why. If I were to make it a square matrix, if I were trying to make this a matrix, these right here, look, I have what? 1, 2, 3, 4 columns, but I only have 3 rows. Well, I need a 4 by 4. There needs to be a system. And remember, in order to solve a system, you have to have as many equations as you do variables. Such as right here, I had 2 variables. I have 2 equations, pretty much, right? Okay, here I have 1, 2, 3, 4. This is like an x1, x2, x3, x4. I have 4 variables. I need 4 equations. I only have 3. So what that means is this really looks something like this. Okay, that last equation zeroed out. Okay, how do we zero out an equation? Well, that last row zeroed out. How do we zero out a row? Well, what happened? 2 rows, we combined them. They were the same exact lines. They were the same exact rows. So one of them zeroed out. Like when I went to get rid of a variable, get rid of an entry, and say I put row 1 with row 4, and look what happened to make row 4. Look what happened. It zeroed out. So somewhere in this system, In this matrix, one of the rows was a multiple of the other rows, and when I combined it, it zeroed it out because I need that square matrix. So I needed a 4 by 4. So since it was able to zero out, that means it was a multiple of something else because I multiplied one row together by I multiplied one row by 2 or 3 or 4, it equaled the other row and then it could zero out. So they aren't independent. They're really the same thing. One of these rows was the same thing as row 4. So these are linearly dependent. If I can turn it into somebody else, then if I can make it look like another row, then it's dependent. If I can't ever make it look exactly like the other row, such as in C, I can't turn 1 negative 4 into 2 10. There's no way I can do it. Even if after I get negative 8 and 10 right here, if I wipe that out, then I've now changed the 1 2 part. Okay? So if you can make one row look exactly like another row, then they're dependent. Okay? So C is independent because I can't make row 1 look like row 2 ever. D is dependent because that whole fourth row is missing, which tells me it's 0 because lots of times math people they don't want to write so much, and there's no sense in writing that zeroed out row, but I know it existed because I needed a 4 by 4. So that 0 row is, they don't write it, but it was really there, which means that we made some other row look like it, combined it, and made it go away. Okay? Now, B is actually going to be linearly dependent as well, and here's why. This is free. This x2 is free, what we call free. It's all zeroed out. We can't do that. We can't have that. X2 doesn't equal anything. It doesn't matter what we pick X2 to be, it's going to work in there. So I can have more than one answer for whatever X equals 2 is. Because this is really 1x1 plus 0x2 minus 2x3. 3x1 plus 0x2 plus 12x3. 7x1 plus 0x2 plus 0x3. Okay? Look, x2 is not independent. It doesn't matter what value of x2 we pick. It's going to work in all three of equations. I can pick 10, I can pick 12, I can pick 200. It doesn't matter. It's going to zero out. Those x2s, those rows are all, it doesn't matter. They're dependent upon each other because of that x2, because it's zeroed out. So if this is free, this is what we call it's free, that's what it calls it in your book, then they are linearly dependent because you don't have an exact answer for x2. You can't get an exact one number answer, so it's dependent. Now, A is also a special case because there's only one vector. Well, okay, that means that in order to get these x1s, 2x1 and 1x1 to equal 0, okay, you're probably going to have to multiply it by some scalar, C1. The only way to do that is if, next this, because this is a scalar one, my bad. You're going to have to, in order to get that to equal 0, C1 is going to have to equal 0. Okay? Because, well, C1 is going to have to equal 0 because there's no way we can get it to be anything but that. Okay? And it's a little confusing because I did write 2x1, 1x1, and that's not what we're really doing there. Okay? This is where you have like A, well, no, You just have a scalar times a vector is what it is, because there's not a system there. Okay, the only way you can get that one little equation to equal 0 is if you multiply it by 0. Okay, let's see. All right, I think that pretty much sums it. Oh, so they are, I'm sorry, it is linearly independent.